Let's see where we left the last time. So we are still in chapter 3 of the textbook. And chapter 3 of the textbook, it goes over
Professor, just one question.
Of images and also the spatial filters or spatial filters. Now, last time I think we were discussing about we talked a lot about actually here in this slide we just went over very briefly. We said that we can analyze the images by using the bit planes, but we just skip this one very fast. Now, I just want to go over an example which follows. Yeah, I think this would be the part that I might go over. So let's assume that we know that we can have images that can be recorded in different resolutions. So traditionally, often, which is enough at least for high resolution images, if we want to print, let's say, a high quality magazine, 8-bit could be good, 16-bit could also be way better, but 8-bit is enough. And now the images, we can classify them based on the bit plane. Now, what we mean with this is, for example, we see this image, and in this image, we have the very first Q-magic concept, that image is the grayscale image. And then the other 8, they are the representations of each bit that is in the image. Now, what I want to say here is that let's assume that we have a 4-bit image, but it's 4 by 4. Now, 4-bit, it's something like the value. Actually, meanwhile, can I have someone speak? Are you listening to me? Is everything okay?
Yes, we are listening.
Okay, thank you, Ari. I mean, when I'm the only one, it feels very weird. Okay, so and now let's assume that we have this image 4 by 4. Of course, it's not huge. It's 4-bit, and 4-bit is 2 to the power 4. We get 16. So we have 16 different quantization levels. And now all of these numbers or intensity values that will be allocated for each pixel in this case, we can write them as you can see here on the slide. Okay, so over there you have 16-bit representations of the numbers from 0 to 15. And now, once you look carefully there, we have the most significant bit. Now, what is our understanding for the most significant bit? I'm not sure how well you can see the board right now, but assume that we have 3.1415. Now, the most significant bit is this one, or is the digit, the significant figure after the comma. That's the most significant bit. But the least significant bit is this one. Okay, so if you want to have high precision, it really matters whether we write the pi 3.141 or 3.145. Okay, so this adds the sensitivity. Okay, so it's very sensitive. And the least sensitive bit is this one. So you can write this one 3.14 or 3.2 or 3.1. This is doing, or imagine this one, from 3.1 to 3.2, the change is huge. Okay, so that makes it the least significant bit. So this would be the first bit in this plane is the most significant. The least is the 4th bit. And now the least significant bit, it quantizes the whole range in 2 levels. So let's have a look at all of these 16 numbers. They have the bit representations as they are shown. Now, if you look at the first column, what do we see there? We see that half of the numbers are 0 and half are 1s, okay? Which means that if we just look at the least significant bit, okay, what being 0 and 1 means, it means that we can separate all the numbers smaller than 8 as 0 and larger than 8 as 1. Okay, so we do a threshold, which is right in the middle of the, what's the name, of the whole range. So for example, and the most significant bit, in principle, if you look at the most significant bit, it goes 0, 1, 0, 1, 0, 1 continuously. Okay, so it's like what is determining whether the numbers are even or odd, including the 0 as even. Okay, so this is how, in the broad sense, that's what they determine. Now, this image that we have here, which is 0213, the bit representations on the other side of the slide, and you can see that the very first number is 0, which is 4 zeros. Then we have 2, which is 0, 0, 1, 0. Then we have 1, 0, 0, 1. Then we have 3, 0, 0, 1, 1. And then the fifth element, we start reading column by column. Okay, so the bit representations, you get the first column, then the second column, third column, and so on. So these are the bit representations of this image. And now, these in red, these pixels that are here in red, they are larger than 7, okay? So these, which are black and red, they belong on the least significant bit. If you look at the right side of the slide, they are larger than 7. So this least significant bit would represent, if we write just the fourth bit information, this is what happens, okay? So we write this one as, we quantize the whole pixel intensity. We put a threshold saying anything larger than 7, count it as white. Anything smaller than 7, count it as dark, okay? Now, this is the fourth bit, the least significant bit. Now, if you look at the other bit, the third bit, which is like, which can be, you can see, actually, if you have a look at the third bit in the right side of the slide, if you look carefully, you can see that what it does, every 4 elements, it goes 0, 1. So the first 4, they are 0. Then the next 4 are 1. The next 4 are 0. The next 4 are 1 again, okay? So in principle, what the fourth bit is doing, it's separating, I'm not sure how well you can see the slide, but it looks like the fourth bit, if we have the whole range from 0 to 15, the fourth bit is separating, it's having a step function, which is 1 here, okay? So this is the fourth bit. The third bit is doing this. It's separating this range into 4, not into 2, in 4. And the first quarter is 0. The next quarter, so this is 0. The next quarter of the domain is 1. Then the next quarter is 0 again. And the final quarter is this. So this is what the other bit is doing. Then the second bit, if you look at the column in the right of your slide, we can see that the numbers over there, we have 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, which in principle, this means that one can separate this domain once more. So we separate it again in blue, and the first 2 are 0. Then we get 1. Then we get here 0 again. We get 1, 0 again, 1. So this is what the bit, this is what the third bit is doing. And the last bit is just going 0, 1, 0, 1. Just each time the pixels change, the pixel value changes from an even number to an odd number. Okay, so this is the last bit. So this is the first, second, third, and the fourth. Now imagine that the 3.1415, the least significant bit, is the 1, the 3.14. The most significant is the 5 in blue. And now the thing is that the whole range that we're dealing with, it can be divided in 2 to the power 4 minus n plus 1. Now n, in this case, 4, we use 4 because the 4, it's 4-bit image, this one that we have in this slide. Minus n, it represents the bit that we are analyzing. Okay, so if we want to see what the fourth bit does, and we want to see in how many ranges we want to divide the whole range, in how many sections we want to divide the whole range, we see that for the fourth bit, we have to divide it in two different domains, 0, 1. Okay, so we put the threshold right in the middle. If we have for the third bit, the information that the third bit is carrying, it can be divided in 4 domains as we showed it on the board. Okay. Now there might be specific images where, for specific that are required at for different reasons, where specific bit layers, specific bit planes, they have much more information. So these techniques, they can be used also when we do image compression, where whole bit planes, they can be discarded completely, and we can use less of the bit planes. So now this is last time we just skipped this part, but I think now it's a little clear. So now there's the same image, and we see here that is the first same image that we had. Sorry, I cannot, maybe I just stay here. So this is the image that, which was 2 slides before, 2 slides ahead. And this, we can reproduce the image as the first one. It's including just bit plane 8 and 7. The second one is 8, 7, and 6. And the third one is 8, 6, 5, and 5, and so on. But if we use only the bit, the 0th bit, or the least, the most significant bit, all we see is we're going to see this one. So we're going to see this one at the bottom, because this has all the noise, okay? But we don't want this. These are more helpful. So this one would be enough, which means that 8-bit plane, 7-bit plane adds some more features. This one also adds something, probably also this adds some detail, depending on what is the precision that we want to see. So last time, I did not have a well-prepared example so that we could go over. That's why I skipped that one. And then last time we talked about this, the histogram, where the most important aspect was histogram equalization, which in principle, this was also in line. So from the recordings of last week, you can see actually we also did some examples, not only spreading out the histogram by using histogram equalization, but we also took the image to we did the gamma transformations. And the gamma transformations, what they were, we just took the pixel intensity to the power 1, 2, 3, and so on. And then, actually, where are these? I thought the gamma transformations, they were somewhere here, or probably I just showed them on using the MATLAB. So then we discussed the convolution and the correlation, and the correlation and the convolution. What the major difference between these is that when we do when we talk about correlation, we have 2 signals that we just merge on top of each other. Okay. So if we see here, if the filter is this W, which is 1, 2, 4 to 8, they are just put on top of it, and the filter hovers over the image. The convolution, the way to think about convolution is that you think of these as if you have 2 Gaussian functions which approach to each other, okay? Which means that when let's say that you have 2 Gaussians, one is moving slower, the second one is moving faster, and is going to catch up. When they catch up, you start multiplying them, but you multiply the last element of one Gaussian with the first element of the other Gaussian. So that's why we rotate the filter. So before we do convolution, we rotate it by 180 degrees if it is one-dimensional signal. Now, in order to analyze these, we often use discrete unit pulses, or we can even call this the delta functions. So in signal processing, there are some delta functions which have an infinite height, but they have a thickness which converges to 0, down to 0. Now, in one-dimensional correlation of discrete unit pulse, DUP, we reverse the kernel by 180. And then I think in 2-dimensional, we rotate the kernel with respect to the 2 orthogonal axes. So for example, here, this is an example of 2-dimensional filter which convolves or correlates with the DUP, discrete unit pulse. Now, the correlation and the convolution, they have different properties, which are shown here. And we are lucky, we're going to say some more words about the convolution, assuming that we have different filters. And these properties, we'll mention these again. And now we see here that the filters, I think we stopped somewhere here in this last time. So we have 2 types of filters that we can see here. One is called the box filter, which is simply an averaging filter. Okay, so what this means is that if you have the box filter all once, this goes over a certain pixel, and what it does, it sums. So we do element-wise multiplication. Element-wise multiplication. All of these ones multiply the pixel values in a window of 3 by 3. This could be even a window of 5 by 5 or 7 by 7. And we add those and we divide by 9. We need to normalize it by 9 so that an 8-bit image will still fit into an 8-bit assigned variable. Okay, so if the maximum pixel intensity is 255, or let's say 200, if we add 9 of these, the image will get saturated if we just add them up 9 pixels without dividing by 9 again to take the average. So this is called a box kernel. Box kernels, we assume that they are averaging kernels. Then we have also this other kernel, which is a Gaussian kernel, which is something similar. In the homework, I guess you had to construct a function which looked like a Gaussian in a much larger range, actually. But this is how it looks like. This is the code that you can use where M, for example, this is what you see here. It's a Gaussian kernel with dimension 3, sigma 1. And what do we have here? A spatial, so there are some synonyms, a spatial filter kernel. This is called a convolution filter, convolutional mask, or kernel again. So these kernels that we can see, this is how they look like. Here, this the kernel, which has a dimension up to 17 by 17, it has a large sigma, but then on the right side of the slide, we show 2 kernels which are 3 by 3. If you read the x-axis, it has the size of the matrix, which is going to convolve with a certain image. If the matrix is 3 by 3, it looks like these two, if the sigma is 0.5 and 1. So if the sigma is 1, it looks like really, if we plot it, it's really discrete, it's a little wider. Now, the kernels, now when we deal with kernels, what happens is that, as you can see from here, images, in order to get a higher resolution, imagine for a moment that we may want to have an image which is 1000 by 1000. Okay? So this would be 1000 by 1000, which means that the number of pixels, so 1000 is 10 to the power 3, and the number of pixels overall is 10 to the power 6. And now this 10 to the power 6 pixels, if we use a kernel, and if the kernel, it's let's say 3 by 3. Now 3 by 3, it's around 10 multiplications if we are going to convolve this one with an image, and this is approximately 10. 3 by 3 is 10. So overall, this is 10 to the power 1. So overall, the number of, if we want to consider the computational complexity or the time that one computer needs to do the convolution of an image with a kernel, this means that this kernel is going to sit on top of this pixel here on the edge, and we need to multiply element-wise all of these kernel numbers with the pixel values. And this means that we have, for each pixel, we have 9 multiplications, okay? And 9 multiplications, we have to multiply this for each pixel. So for 1 pixel, we get 10 to the power 1. For 10 to the power 6 pixels, we get 10 to the power 7, okay? So this is how many calculations one needs to do. Now, what can happen is that this number can be higher, okay? The pixel resolution can be way higher. And also the kernel size, they are not always 3 by 3. The kernel size, traditionally, we can even have kernel sizes of 11 by 11, okay? And if this kernel size is of 11 by 11, once we do the calculations, this 11 by 11, we get 10 to the power 2. So this adds immediately, how much does it add? It adds another order. Now, with all this discussion, what can happen is that these kernels or these filters, they can be separable. Okay? A kernel, which let's denote this one with W, if this is a kernel which is 3 by 3, so, and this is a matrix, we denote it like this. We can write this one as a multiplication of 2 vectors. So if we want to multiply 2 vectors to get a matrix which is 3 by 3, what should be the dimension of the first vector? We know that whenever we multiply m by n, this is equal to a b, which is m by p times c, p times n, right? So in order to get this dimension in the result, these components, the outer components of these, they should be m and n, which means that here we can have a vector x, which is 3 by 1, so this is a vector, times another vector, which is y, which is 1 by 3. So we can multiply these two, and 3 by 3, we get 3 by 3, which looks like this kernel. If this matrix 3 by 3 can be written as a product of 2 vectors, we call this separable. And being separable, what it helps for us is that in this case, if we had a kernel which is 3 by 3, what we can do is that we can convolve a function with the kernel, W, and the number of calculations, it was equal to mn, where the mn can be the dimension of the image, times little m times a small n, right? So here there were both 3. Little m and n, they are the dimension of the filter. So this is how many calculations we need to do. But now, if we convolve the image with this kernel first, okay, with the x, the number of calculations is mn, all the pixels of the image, times 3, times n. Okay, this is the number of calculations. We do those, and after we do those, the image size, it will be the same. Okay? The image size, it will not change, it will still be mn. Then, if we convolve with the other filter, which is the y, the number of calculations would be mn times n. So if we add these two together, we get mn. So this is how many, sorry, this is n plus n. So this is how many calculations we need if we convolve the image with a filter which can be separable. Okay. Now, how much do we gain from this case? So let's calculate what is the ratio between convolving the image with the kernel 3 by 3, two-dimensional kernel, versus applying twice one-dimensional kernels. Let's check for this case. The image, it was 10 to the power 6. This is 10 to the power 6 times n times n times 10, because this was 3 times 3, around 10. This would be over 10 to the power 6 times, this is 3 plus 3, 6, almost 5. So this is approximately 2. So we gain a factor of 2 in terms of number of calculations, only if we express one two-dimensional filter into two one-dimensional kernels. Now, in these separability of these kernels is very important, especially if someone is doing, for example, training with large data sets of images. Over there, the images can be high. They can be at least in the order of 10 to the power 3 by 10 to the power 3. And the number of filters that are applied in each layer of convolution to do the training in convolutional neural networks, in CNNs, the number of filters, it can be up to 512. So one layer can have 512 filters, which means we have a lot of filters. The filter size, it can be anything from 3 to 11. It does not get any larger. That's traditionally how much they are used. But when you talk about these types of large number of computations, having filters which can be decomposed, it can really save a lot of time. So this was, so the filters, and one filter which is decomposable is the Gaussian filter. Now let's have a look at what we have here. So what we can do is that we can have one vector x1 and another vector x2, and this is also like a review of linear algebra. So if we see here, let me try to find where we have this. And to check the rank, the example. Okay, so let's see. What? Wait a second. I think you are seeing this slide. Yeah. So let's see. This is x1. Okay, this is a randomly generated number, a vector, and this is another randomly generated vector, x1 and x2, and then we can define a matrix A, which is we can write it like this: x1. x2, okay? So this would be A. And A, if we check the rank of A here, it's 2. Now, this is the rank of 2, and we can also define A, which in the first row, it has vector x1, in the second row can have vector x2, in the third row can have vector x1 plus x2. So if we check the rank of this matrix, now the matrix A, it's 3 by 3, okay? We have the first row, second row, the functions that were randomly generated, And the third row is the summation of the first two. So we have 1 plus 4, 5, 3 plus 1, 4, 1 plus 5, 6, and so on. But since the third row is linearly dependent with the first two, which were randomly generated, the rank of the matrix is 3. Sorry, it's 2 in this case. Now, this is equivalent to, if you remember from linear algebra, that if we generate the reduced row echelon form, what the reduced row echelon form does, it counts how many, if you have many equations that you need to solve, you can write all of these linear equations into, you can write the coefficients of these linear equations into a matrix, and then we get the reduced row echelon forms to find out how many rows are linearly independent of each other, okay? Or to find out if you have any redundant piece of information. For example, in this matrix A, the third row is redundant, is useless, because everything you need is already in the first two. The third one is linearly dependent. Now, good. So now we remember what we knew before regarding the rank of matrices. And now one thing which is in the theory of the filters. Sorry, we have it here. So a filter, it is separable if the rank is 1, okay? And the rank of a filter is 1 if it can be written as a product of one column and one row, okay? So that's all we needed to do. That's why, sorry, not here. That's all that we wanted to go over. So let's see here. If we do, so A was composed of row 1 and row 2, x1 and x2. But now let's make the B, let's multiply x1 transpose with x2. And let's remember what was x1 was this, x2 was this. So we multiply x1 transpose, which makes it 3 by 1, multiplied by x2, which is 1 by 3, and we get the B. And the rank of B, according to our definition of linear algebra, should be 1, and it really is 1, okay? It's 1 because, so it looks like B, if B is a filter, so we can, let's look at B is. So the filter can be anything actually, which means that if B is a filter, when we if we convolve this one with any image, this would be equivalent to applying first x1 and then x2. Okay, so this is what we wanted to say regarding this. And also, what we can try, let me see if we have this here. Yes, okay, so let's assume, let's clear out some variables. Now, it may be imperative, we also discussed about this one, so we can generate a Gauss filter. So let's evaluate selection. So Gaussian filter 5 by 5 with a sigma, standard deviation of 1 and amplitude 1. This is what it is. So if we want to see how it looks, I think by now you already know how they are going to look like. So here we have a 5 by 5 kernel with a sigma 1. This is how it looks like. And what we care, well, we care about two parameters. The first one is what is the rank? Apparently the rank is 1. And if the rank of this Gaussian kernel, Gaussian filter is 1, it looks like we are lucky. We can decompose it into two vectors. And also, by using this function, sum of W, we can find what is the sum of all of these numbers that we see here. And it looks like it's 1. It should be 1 because it should be averaged out. Okay. Then, so this is something regarding the filters. Now, here you have some. I included here the code. You can run the same thing on your own on any image. But let's see what we have here. It looks like the first image is the test pattern 1024. That's the size. It's 10 to the power 3 by 10 to the power 3. First, I just check what is the maximum pixel value. Okay. Then we can generate we have a Gaussian kernel which is 7, a size of 7. We have a Gaussian kernel which is 17, and then we have figure 1, figure 2, figure 3. They represent 1, 2, 3. You see whatever the slide here denotes, it's this, this, and this, which it looks like if you apply the Gaussian filter, actually, if we zoom in even on these images that are here, even from the slides, we can get these images, stretch them out, look carefully in these regions where we have little dots. You're going to see that even the Gaussian filter is going to affect somehow the pixel distribution around here, okay? When we have this like noisy section. And then Here, W3, it's a filter. If you see this W3, it's a filter which is a box filter, which is a lot of ones, which means that it's going to average some elements. And if you look here, figure 5, it shows the image, and figure 5 is the fourth image down here. And it can really be seen that it's a little more blurry, okay? Because it has averaged some wide high values with very low values. So it's smoothed out. And then this, if we use, so this figure 5, it uses a box filter, 17 by 17 ones, and we see this result. But if we use a box filter with 37 by 37, we get this image, which is the image 6, which is on the very right side of the slide. And one thing which can be noted is that if we keep increasing the number of filter, especially for the box filter, we do get a dark contour on the outer borders of the image. And this is because since the image is 37 by 37, we need to do padding. And if the padding is 0 padding, that means that the edges of the image, they'll be averaged out with a lot of zeros. That means that it makes darker at the edges. Here we have another example. Again, you can also read it from the code what we are doing. So we read first this image, which apparently it has some stars which are distributed around. And by the way, if anyone likes to take pictures, the last 3 days, including tonight, I guess, Jupiter, which is the largest satellite of our solar system, will be in line with Venus, and you can see it together with the stars, okay? They look like yellowish. Venus has been around a month. Even tonight, actually, you can see it. Sometimes from 9 p.m. to 12 p.m., it will go direct from Tirana to Durrës, and you can take nice pictures if you really, and you can see that because it's moving much faster than the stars. Stars don't move, this moves, and here we have an image which apparently has a lot of stars, and stars, they have very less pixels associated with those. And what we can do is that, let's see what we did. So we have developed a filter which has box filters 3 by 3. We have a box filter 15 by 15. And if you notice all of these, sorry. So we have box filters with different size, and it looks like larger the box filters. That means that we are averaging out with a lot of pixels in the proximity. And what happens is that we get something which is way blurrier. But actually, this can be also, which means that we lose some white dots or stars. But this might also be something good, because we can apply then a threshold. So if you look these two parts of the code, we can assign for these images, especially the images which are blurred out, not the initial ones, we can put a threshold something around 180, and any pixel larger than 180, you can assign it as a white spot, 255, maximum of the 8-bit image, or anything smaller than 179, you can assign it as 0, and we get this image which is at the bottom. If you use a threshold a little lower, around 115 or 114, you get this other image, which means that you get some other content of the original image. But now, these are all ones, and it's much easier to quantify this. Okay, so if you just add up the pixel values, you can make this 255, you can make them once, you calculate the sum of all pixel intensities, and you can count how many pixels have stars or some other components, and how many don't. Now, these were box filters applications, which you can, this is just an exercise. Then here, actually, what we see here, even in this slide, what we are really doing is that if we have a box of 3 by 3 and 15 by 15, so we're trying to do the averaging. Now, this can be represented in the spatial domain by this graph, which is this U0. It's a function with a specific amplitude. And each pixel, we go to the center of a pixel, and you can assume that this is like a step function 1, and it's averaging out the pixels in a proximity. Pra ky funksioni, si përgjatë x-it, mund ta mendoni sikur ka një gjërësi 3 me 3, ose ka një gjërësi 15 me 15 që pa të ky shembull këtu, dhe ajo që bën mbledh mesataren. Pra, dhe kjo është, si ta quajmë, Here, since this takes the average, you might assume that if you are taking averages of one white pixel with a dark pixel, you find the average. And once you find the average, you remove high frequency components. So normally at the edge of an image, we have high frequency components because high frequency is something which is considered to change abrupt in time or in space. Okay, so something changes fast, that means it's high frequency. So we like to keep edge information intact. So if it is black and white, we want to be like that. If we take average, we damage it, so we remove the high frequency. So in principle, this is called like a low pass filter. In spatial domain, averaging the pixels is like a low pass filter, which in the frequency domain, this can be represented by this other graph on the left side. So this is equivalent to taking the signal, which in this case can be an image. We calculate the Fourier transform, and then we multiply with a step function, which is 1 close to 0 and 0 above some threshold. Okay. Now the thing is that this graph that you see here is not really good, because there is something very wrong with it. Not very wrong, because in the frequency domain, all the filters are symmetric with respect to the center. Okay, so we're going to see this one in chapter 4 of this textbook, and you see really good application of these frequency filters or filters in the frequency domain. So it's also written here, all filters in F domain, they are symmetric with respect to the origin. And let's see what we get here again. Here we see some other examples. We have low pass filtering with different with using box kernels. So actually this is the same as this is just another exercise with what we saw a couple of slides before. And these box filters and Gaussian filters, what they can represent, if someone is taking an image from a camera or from a microscope, box filters, the way that the output of the image gets out, it might represent the characteristic, the blurring of a lens. Okay, so if there is blurring, you show it with box filters. But the Gauss filters, it can be used to represent a defocused lens. So if a lens is not focused, you see a smooth and almost acceptable type of image. So I just wrote it here. So if anyone is interested, you can keep this as a reference. And now here we see. Now, to understand a little bit the construction of the mathematical relationships of the filters, it helps us to understand what happens if we apply, for example, several filters again and again on the same image. Or any one of you who is ever going to use several filters, it doesn't have to be an image. It can be one-dimensional signal. But if you apply a kernel again and again, something happens. And a few slides that we're going to have today, we'll try to make it a little more clear how the variance or the standard deviation of a certain filter changes, assuming that we don't have box filters anymore, okay? Because box filters, they don't have a standard deviation, or they have an infinite standard deviation because they are flat. But anything which looks like a Gaussian, it has a limited finite sigma. So here we have the filter. This is how a Gaussian filter looks like. Its k is the amplitude, exponential, x squared, y squared, etc. And now, if the data that you are analyzing is an image, we know that we are jumping from one pixel to another, which means that we are moving 1, 2, 3, 4. This is how we are going. And this 2, when you calculate the square of 2, it's 4, plus another 2 squared plus 4. That means that these r square values, they are always integers, okay? And the distance where the pixels are from the center, unfortunately, they are not very high precision, because many square roots, they are irrational numbers, which makes them, but we can, so what this tells is just telling how far a pixel is far away from the center. Now, we may need to know that, because, and when I was making this slide, if you notice, I was trying to make these symbols in sigma, and you can even you can have like a small exercise. The second line in this slide, how would you read it? I know Ari knows how to read it, but I'm not sure if Nicolene knows how to read it. So what is the second line telling here? I hope not all of you are asleep at the same time, okay? Can I have some verbal confirmation if you are really...
We are here, yes.
We are good, okay.
Here.
Okay,
Here.
so... Oh, Ari, ti lexon të besoj, të very small?
Where?
No, I'm
There.
asking about this part. What do you read from here?
O R.
How do you read this part?
I think that's an O A R or
Well, this is sigma S. This is
yes.
mu. It's M,
Mu
M, alpha A, and lambdas are L.
and both else. Yes.
Okay, so this is
Oh, very small.
Yeah, very small. Yes. Okay, so yeah, they are very small. Okay, but that's something for you to notice. Now, what we are trying to show here is that if you remember last time, we said that if you have a Gaussian distribution, if one data it's 3 sigma away from a Gaussian distribution, this represented something like less than 0.5% of the data. Okay, so last time, just I hope we can. I hope you can see this part on the board. But if this was 1 sigma, because this is where the sigma is found, we have 68% of the data. Okay? If you go far away, plus minus 2 sigma, here we get something like 95% of the data. This is plus minus 2 sigma. Plus minus 3 sigma, we get 97 or 99.7% of the data, which means that if we are 3 sigmas or 4 sigmas away from the center of a Gaussian filter, these values are almost 0, okay? So the value of y, what I'm trying to say in the second line is that for x, which is larger than x0 being the center, plus 3 sigma, if you are further than from the center, 3 sigmas, the values of y, they are epsilons. They are negligible, okay? They are almost 0. So if you add into your calculations some zeros times some numbers, it's meaningless, which means that a Gaussian kernel, if you construct a Gaussian function for any one of your calculations, if your sigma is some value, don't make so if the sigma is 3, don't make the kernel 500 by 500, okay? Because if sigma is 3, you multiply it by 6, you get 18, you add 1 to make it the odd number, 19 is good, okay? So here you see on the fourth line, if the sigma of your Gaussian that you want to use, if it's 4, you multiply it by 6, assuming that you have 3 sigmas on the right and 3 sigmas on the left, and you get a 24. You add 1 just to make it odd number, you get 25. So that makes so what we're trying to say here is that if you know what feature you want to pick up, so let's say you have an object or you have a signal which has some radius or some diameter, and you want to filter that out. If you want to filter that out, then the sigma should be in the range of that object. We'll see an example a little later. And then if the object is 10 pixels, then you also make, if you want to filter this object, the sigma of the Gaussian kernel can be 10 pixel too. But then you multiply this 10 by 4, which gets, no, this 10 sigma multiplied by 6, you get 60. Make it an odd number, you make it 61 or 59, would make a good filter. Okay. Now, here we see some functions, or assume that we have 2 Gaussian functions. Gaussian functions, they have very, very beautiful properties. And when I was a student, I forgot many things, but the last thing I would forget in my mind, it was this concept, that the Fourier transform of a Gaussian function is still a Gaussian function, okay? Many functions, you take a Fourier transform, they look different, they look like butterflies, meaning that the frequency spread differently, but I'm not saying that you're going to forget it, but if you're going to forget this thing, the last thing you should forget is that the Gaussian, the Fourier transform of a Gaussian, it's a Gaussian. So that's one nice property of these beautiful functions. Also, another important property of Gaussian function, we talked about this one before, it's separable, so we can represent it as a multiplication of 2 vectors, 1 column and 1 vector, and we get a square filter. And what we see here, actually, we see that if we have 2 Gaussian functions, there are 2 beautifully looking functions, which are smooth, differentiable, etc. And if these have specific mean, if the average value is mf and the average value of mg, or 2 functions f and g, if these are shown here. Once we multiply these functions together, the mean of these new functions, it will change given these values here. And if we do the convolution of these functions, the mean, it will be mean of f plus mean of g. Now, considering the standard deviation, can you do this exercise? So assume that function f, it has a sigma of 3 and g has a sigma of 7. Can you calculate what should be the sigma of the convolution of these two functions? Am un algorithm impact? Equațiunea ne keni të ky slide. So you just
Wait, so the sigma of the first one is how much again? 3 and 7?
The first sigma of function f is 3. The sigma, which means standard deviation of the second function g, is 7. So imagine you have 3 and 7. And we are asking, what is the sigma of convolution of these two filters?
Square root of the sum.
Which means, like, tell me something, which is?
Square root of 58 is 7.6.
Okay, that's right.
According
so
to Google.
7 squared is 49, right?
Yes.
Are you sure? Are you?
7.
No.
I googled it. Square root of 58.
In Albania, recently 7 times 7 is not 49. It's not always 49. But so let's see here. 7 times 7 is 49 plus 3 squared, 49 plus 9. We get 58, right? Okay. Is it what you got, Ari?
Yes, square root of 58. Okay. 7.6.
Okay, but 7 times 7, you know what it is. It's 49. Okay. So let's go to the next slide. Now here you have a small exercise which you can, which what we do here is that we assume that we have a signal. We want to have a sigma 3 and another function with a sigma or standard deviation 7. And we want to have a kernel of 49, okay? We generate a function here, W1, which is the first figure, which has the highest amplitude, which is 0.018. I hope it's not almost very clear. So we have this filter, and then we plot it. Then we generate W2, which is another signal. So shikonet block in the code. The second block, it says W2 is equal to Gaussian kernel, n with sigma S2. And then we plot it on the figure 3. Then what we do is that in the third part of the code, we multiply these two functions, okay? So what these two functions, let me think for a moment. No, actually, I was not, spend a minute. Do you understand what this code is doing? A mund ta shikoni pak? So actually, what we are trying to do here, first thing is that we are generating 49 by 49 Gaussian kernel, which is something like this, and it comes down this way like this, okay? And this is 49 rows and 49 columns. So after we generate it, what we are doing is that this f it's reading the 20. So what is n divided by 2? It's 49 divided by 2 is 24.5, right? But if you use the same function, which means that 24.5, we get 25. So if we get the 25th row, we're getting a function which looks like this, okay? So this is how, if you look carefully, we're extracting the center line. So from a two-dimensional filter, we're taking out the mid row, okay? And the mid row is the 25th row. We get it from W1 and W2. And what we are doing, out of here, we get that one on the figure 1. So we get this function with sigma 3. Then we get another function with sigma 7. And a function with sigma 7, the amplitude is much lower, okay? Because it's much more spread out. And if you look at the figures, the amplitude of sigma of f is like 0.018, but the other one is 10 to the power minus 5 or 10 to the power minus 3. Then these two functions, we multiply them and we plot them how they look like. and you can use this as an exercise. You can run the same code which is provided here in this slide, okay? And you can check what is, once you plot the functions, the multiplication of two Gaussians, it will still look like a Gaussian, probably a little bit distorted, but you can, so what you found, 7.6 RE that you also calculated, you can see from these graphs that really the standard deviations of the convolution of the filters, it's what the formula says. Okay, it's good to confirm this sometimes, but you can play around with other values of sigmas. And the convolution of these two functions, f and g, in this case, let's not forget, f and g now, let me think, no, this is the convolution of the two filters. Im filter, W1, W2, the last three lines of the code. Now, we can run we can play around because everything is ready, but probably I'll just pass this one. And here we have some using Gaussian filters on images. I think we did this one. And in this slide, what we see here, okay, here there is something interesting. We have this image, this test image, which is shown, which can be used often for in the ophthalmologists, how they are called, the eye doctors. We can apply, so the A is an original image with a Gaussian kernel of 43 by 43 with sigma 7. Then the second image, it's the same sigma, but we have a different kernel. Okay, the kernel is much larger. What we said before, we said that if the sigma is 7, how large can the filter size be? We said that it is 7, we move 3 sigma to the right and 3 sigma to the left, which means that we have six sigmas. So 7 times 6, we get 42, plus 1 to get 43, so that we get an odd number for the filter. And then we said that if we get a little further, the values of y will be 0. If that was true, well, they are not 0, they are epsilons, right? They are very small, but they are never 0, because a Gaussian function is 0 at infinity. Okay, that's when mathematically speaking. So it looks like if you apply the same sigma, but different filter size, 85 by 85, that's the image in the middle. If we subtract these two, what we see is that image that is over there, okay? And it looks like the difference, it will be mainly at the edges, okay? So the edge information, it's there if you want to enhance something. Now, based with this idea that we see here, we can apply this here. There is another example. Okay. So here we have another example. So if you have a wide object and a step function, and we convolve this one with a filter with a specific size, what happens with the step function? It becomes like a Gaussian, okay? So this step function, it becomes like a Gaussian because we keep averaging a small value with a large value. Here we have another example. This is just here again, this is like an example but it's just a different image, okay, a different photo. I guess, yeah, it is different. So a few slides before, even had the code, so you can test with different images. Here we have a nice exercise where we try to extract the background out of a pattern. So now a problem in image analysis is the non-uniform backgrounds or non-uniform illumination. So if we see this, the first image, we see that the one edge is brighter and the other edge is darker. And what we can do is that we can apply a Gaussian filter. I guess I even have the code. Can I check? No. Oh, I don't have it. I thought I had it. Okay, anyway, I thought I had included the code and they're running with different sigmas. Apparently, I don't have it here. So what we see here is that what we can do is that these boxes or these squares, which are black and white, first thing that we need to do is to determine how many pixels they are occupying in the image. Now, if we, in the example that I thought I had them, but I think I'm going to share with you the code which is in, which I tested this initially. If the boxes are 64 pixels, that means that we can apply a filter, a Gaussian filter, which has a size 4 times larger than the object that we want to pick out, okay? The reason to do that is that we really get a blurring, but a blurring which blurs out regions which are larger than a single box, okay? So if we do that, which means that if we take the Gaussian convolution of this image, which is full of white and black boxes, but which has a non-uniform illumination, we get the image in the middle. And then if we divide, this is really division. 6 by 3 is equal to 2. If we divide the image on the very left with the image in the middle, we get the image on the right side. Okay, so which we see that we can have a background correction. Now here we have other. Let's see what we have here. A circuit board, which and we have a good picture, but it has some noise, which is called the salt and pepper noise. And this salt and pepper noise, we can remove it by using Gaussian kernels. So Gaussian kernels, they can be good to remove that type of noise. And yes. Allow me to have a look here. So these filters that we saw so far, they were mostly we call these linear filters, and they are linear filters because they average out certain pixel values, and one of them was Gaussian, the other one was box. But we have some other filters which do a much better job into preserving the features in a specific object. And these filters, they are median filters. What a median filter does is that if we have 13 values, so let's say that we have a box where we select, and so let's say that what the filter does, let's assume that the filter size is 3 by 3. If it is 3 by 3, then that means that the window that we are analyzing the pixels, it's 9, it includes 9 pixels. So this box, it defines a region, and then in that pixel in the center, we write the 5th largest pixel intensity, okay? That's what median filter does. So it gets all the pixel values, intensities, from 0 to 255, and puts them in order from the smallest to the largest, and picks out the 5th one. If the kernel is 5 by 5, that means that we have 25 pixels analyzing, and then the median filter, what it does, is that it's going to write down changing the value of the pixel intensity at a specific pixel, and writing down the 13th largest intensity. Okay, so this is the median filter. Median filters, it's a nonlinear filter, and nonlinear filters, they are very good because they preserve high frequency content, which means that we preserve the edges in a specific image. Wait a second, sorry. I have a student contacting me. Okay, so that's what median filters do. And in the meanwhile, let's see this example. I thought I had this on the slides, but I guess, okay. If you have any comment, here, okay. And actually, we are a small class, I think. I was wondering whether we should take the attendance, and attendance would just include everyone writing a 1 over there, okay, in the comment section. Like me, I am present, you are here. I do this one for larger classes in the order of 80 students when I cannot follow up very carefully. But now let's see this example, what we can do. So let's see. We have let's evaluate this. So we read this image of a cat. We have this image, which apparently, after we read it, we can see it in the workspace. It's 428 by 590 by 3. So it's a three-layer image, which has the red, green, and blue layer. And this one, we can make this one into a grayscale image. So we get here I2 is now, if you can see in the workspace, I2 is 428 by 590. It's a unsigned integer 8, which means that the maximum value of I2, if we write it here, max of the I2 is 255, okay, that's the highest pixel intensity. Then let's have a look how this looks like. And this is the image of a cat, okay? So this is the image of a cat, and then we can determine two values, m and n, which can be the what's the name, the filter size, and let's try to apply a median filter, but with the size m and n. Let's evaluate the selection, and as we run this, it's still running. Okay, so it looks like the image is not a very large one. It's applying neighborhood operations. I guess you can see this. Really time-consuming. Okay, we're lucky that it took 23 seconds. Okay, that's a lot, actually. Now, I wonder if a Gaussian filter would take this much. If it is 15 by 15, no, they don't. Apparently, the median filter is it has a higher complexity. Okay, let's think about this one a bit later, but you can work this one on your own. Okay, just compare similar size of Gaussian filters and median filters, and let's see, but it took a lot, actually, 23 seconds. And now, what did we found the new variable I filtered, that was the image filtered with the filter 1. Now, what we can do, we can calculate, so let's not forget, I2, it was the grayscale image, which is shown here. Okay, this is I2. Now, the I filter, let's see how I filter 1 looks like. Let's plot this one on figure 2. This is the filtered image. So if you compare these two, it looks like the second image is it's blurred out. Okay, it's not as clear as the first one. Now, what would be the use of these kinds of images? Let's see what we can make use of them. And now the difference, this diff, is the difference of figure 1 minus figure 2. Okay, so we're taking a mathematical simple difference of this and this. And if you watch carefully, you can see actually, can you see the edges of the figure 2? They are dark because apparently the 15 by 15 pixel, the median value, so once it goes here in the edge, imagine for a moment, if you have at this corner 15 by 15 pixel, 3/4 of the values are 0 because the padding is 0, right? So if the 3/4 of the pixel values are 0, the median is also 0, okay? Because we put them in order, we have like 1/4 is non-zero values, then the next 3/4 are all 0. The median, for sure, is going to be somewhere in the middle, which is another 0. That's why you see dark edges here, black edge here, and also here the edge at the tail of the cat. You get some more exaggerated black regions. But good. So now, if we take the difference between this cat and this cat, the median filtered one, and if we let's try to see what we observe. That's figure 3, show the difference. Actually, the difference, you can see some contours of the cat, and it's really, actually, this one, we can do this figure 33 to expand a little bit, to stretch out. Okay, no, apparently it's not, we cannot get it any better. Okay, but I hope you can see, can you see these features of the cat in this image? Yes, okay, thanks. Yes. So, okay, so there's a difference. Now, what we can do is that this image, which was in grayscale, we can add the differences. So these little differences, which they were over there, we can add those, and we get a new image. Now, this can constitute, on figure 4, we have this cat. Now, what can you tell me if you compare this figure 1, which is the initial grayscale of the cat, and this is the initial grayscale of the cat plus the difference between the original image and the filtered image. Do you observe any difference? Maybe the Google Classroom Meet software, I don't know, can you see a difference somehow?
Yes, a bit. For example, near the lighter part of the tail, not the black stripes, the lighter ones are a bit clearer, sharper in figure
Sharper,
4.
okay, yeah, they do look sharper. Actually, what is happening here is that, and by the way, I apologize, but I think a couple of times I've used the board, but I never stopped presenting. And I think that's the part of the course where you should warn me. Kur kam përdorur drasën, s'keni pa gjë besoj, ja?
Ishte pak larg.
Ishte pak larg, po jo, okay, do të kujtoni po, s'ka gjë. Do të kujtoni sepse unë harroj kur kaloj nga drasën në slide, but what we are doing, imagine for a moment that we have a function like this, okay? When you're applying averaging or specific filters, what is happening is that we are averaging some values here on the corner, okay? And what can be, we can observe some edges like this, okay? So we see no changes around here. But then if we add these two together, these extensions, sorry, no, let's assume it's something like this, or let's put this somewhere here. So what we are really doing, at these edges, we are adding the contrast. And you were right, we observe that they are, so you are seeing settings. Let me change something back. So let's go back at the, am I presenting the, okay. I have to select here. So if it really, at least it looks like sharper, especially probably in this region, the front part of the cat. And to test whether that's really true, let's try to do this. So let's check once again. I2 is a grayscale image, and the I new is the image which is acquired by the grayscale plus the difference which was obtained with the two steps. And let's try to crop a region from I2. So let's try to crop something out of there. And I2 is the, wait a second. I2 is a grayscale, but to me it looks like I'm not getting the I2. Did I make, can I try this? Allow me to do, oh no. Okay. I think I2 I have it here. I missed it and now I have to, it won't let me, okay, now I got it. Okay. How can I stop this from? Sorry, I need to run this again. Okay, pausing. Pausing. Okay. This should not take this much. Pausing, okay, do pause. Yeah. Yes, is simulate loaded? Yes, it is. Okay, apologies again. So let's go back. And let's think up to this part. So together, oh, but it will take 23 seconds. Sorry, it will take 23 seconds to calculate the convolution. Apply neighborhood operation. It was 23 seconds the previous time. Let's see how much it's going to take this time. Okay, so this is figure 4, which we call this one as the sharper one. It is sharper. This is the blurred one, and this is the original one. Which is figure 1. It was the figure 1. It's I2 actually, and I was a little confused because when I was running this. Okay, now the correct one popped up. So let's pick up some region in here. Okay, so we cropped out the region. We call this II with 2 I's, and let's crop something out in the allegedly sharper image. But why does this come out like figure 1? Okay, that's why I was confused. This is sharper, but that was figure 4. Let's see if we're going to get this correctly. So now let's see figure 5. Let's try to plot the histogram of the image which had less sharpness, let's say. This is II. Now let's have a look at these two histograms, so which one, well, I think it's obvious to many of us. Which one do you think it's more equalized, more spread out? The figure on the right.
One on the right.
First one.
Yeah, and actually, I tried. Now I have to check something actually. So are these two regions equal? I picked them out in the similar region in the figure. Okay, and if we look at the sizes of II and III, they are 43 by 51 and 49 by 52. Okay, I tried to pick them randomly. They are comparably similar, but the histograms is always normalized. So it looks like this figure 6, which is coming from the, so let's see what was figure 6. It was picked up from the more sharper image. So it looks like really by doing these operations, we can increase the sharpness of specific images by using filters and then finding the differences, because this difference often it will exhibit itself at the edges. And that's what we care the most. We care the most about the edge information. Okay, so we want to preserve it once, and we want also to enhance it too. Okay, so edge enhancement is a very important problem. And now here, probably it looks like the red is overlapping, overcoming the blue one, or probably we do it like this. Figure 7, im his this, im his this. Let's replot this one. Okay, so here we see that, yes, we have on the background, we have the more spread out pixel intensities, which were really the ones from the enhanced part of the image. Okay, so this was, let's say, let's see actually how much time this takes. This was an application of the nonlinear filter. So we saw a lot of box filters, Gaussian filters, but these are nonlinear filters. But let's see a little bit the complexity of this TikTok. Again, let's call this one I filtered 2 using a median filter, 15 by 15. This is the more traditional evaluate selection. Oh, sorry, we're printing 2 seconds. This took way less. Okay. 2 seconds. The previous one, the first time it took 23, then it took 14, now it's taking 0.04 seconds, okay? But it's not the same code actually, this is more optimized one, Metfielder 2. And apparently, so you see, we're talking about 40 milliseconds. Probably it can get even better. Of course, here it's competing also with several operations that my laptop is doing. Okay, here we got half a second, 530 milliseconds. Okay, so these were some of the let's say important sections of chapter 3. And regarding the chapter 3, I want to okay. So now regarding the issue of how certain data they can be distributed or how the kernels can be analyzed, there is an important concept which relates from chapter 2. There were some sections where we, wait a second, I think they were in chapter 2, where we discussed the probability distributions. And these probability distributions, we were analyzing how specific vectors they were changing. And now, what I'm thinking whether we should go over this example now. Probably we should. And also, I just had a note. In the homework, there was a question regarding the resolution represented in line pair per unit. Just be careful. It looks to me that in the book, it might be a small mistake over there. If you follow the slides that we gave the last time, you might be better off if you use the equation, which is something like 1/2W for the line pair resolution. Just be careful about that. And now I'm thinking whether we should go over
Professor, another thing about the homework.
yes.
The first code, which also had the bilinear interpolation function.
Which had what? The linear?
Bilinear interpolation.
Yes.
That wasn't available, I think, anywhere.
It was not? Okay.
No, it's not a pre-existing function since MATLAB doesn't count it.
Mm-hmm.
It may be on later versions. I have 2015.
No, I think did you check? Then thank you for reminding. I can.
I was actually only using LMS, so that might be the problem.
No, let me see. I mean.
No, it may be in Classroom since I was only using.
I can. We can check. If it's not there, I have to provide it for you. Okay, but. Okay, no, but apparently it's not even here, so I have to include it, Ari. Okay, I can share it either here or in the.
Wherever is fine. That's not the problem.
Sure. I will. Okay, so.
That was the only error that remained after running.
Mm-hmm. How about the rest of the homework? Everything was good?
Yes, I think script 2 is fine, as are the P codes, but those are only used in the larger script, so anyway.
Okay. Yes. Okay, so that was regarding the homeworks. And now, let's... Now, the idea of the Gaussians is that often we care about functions that depend on, that correlate with respect to each other. And I want you to... Probably I can do this the last time. It's really important exercise, or I can solve this one and send to you on LMS or on Google Classroom. Now, let's just see one final thing. Let's assume for a moment that we have three filters or three Gaussian filters where the first filter, it's a, let me try to change something here. No, so let's assume we have a filter which is something like 1.5 and another filter which is equal to 3 and another filter which is equal to 4. So if we have these three filters, which is, let's say, F1, F2, and F3, what would be the standard deviation for a filter W, which is the convolution of these three, F1, F2, and F3? How can we find what's the name, the sigma of this new function? Now, the equations of these, they were in the slides. So if you have the slide in front of you, you can go over these formulas. But the new sigma, it's equal to V1 plus V2 plus V3, where these are variances actually. Okay, so this is sigma 1 squared plus sigma 2 squared plus sigma 3 squared, and these are equal to, you can calculate what we get from here, plus 3 squared plus 4 squared. This is what we have. Now, let me see, if I go to the slides, so whenever you do these calculations, they are not difficult, but it might be best to use the variances. So if you are calculating several filters, sometimes it might get confusing if you use the standard deviations. So if you look at this slide, for example, if you have the convolution, you can see that from here, the sigma of the convolution of two functions is equal to sigma f squared plus sigma g squared. But in fact, you know that the variance is the square of the standard deviation, which means that you can just take the variance of the first function plus the variance of the other function and take the square root, okay? So that's the reason that if you have three functions that you apply one after the other, the sigma would in the end be equal to the sigma 1 plus sigma squared plus sigma 2 squared plus sigma 3 squared, then the square root of all of these. Okay? Yes. Okay, so if you have four filters, then it is just, you add up the variances of the four filters arithmetically, you find the sum, and then you take the square root. Now the calculation of the means is a little more complex, or at least when you multiply the functions, or if you find the standard deviation of when you multiply functions, is if you have three functions one after the other, maybe you can try this as a homework, okay? So imagine that you have these three sigmas that we wrote on the board, and try to find what is the sigma if we multiply these three functions, f1, f2, and f3. Which means that you can use this formula in the middle of the slide, but apply it twice. But it's not as simple as the calculating the sigma of the convolution. The sigma of the multiplication, it looks like it's a little more complex. Okay, so I think this would be all for today. I strongly suggest you to go over the textbook and for the remaining topics from chapter 3. And next time we'll start with chapter 4, which deals with the Fourier analysis of images. Do you have any question? No input yet?
It seems clear so far.
Okay, thank you, Ari. I hope you do fine. And I have to stop because I'm from that I have to stop presenting here. Stop presenting. Okay. Here, for him there, give
There